modeling. So for sequence modeling, right, it simply is just RNNs, but now instead of using the basics of theory RNN architecture, we are actually combining two RNNs together to form a sequence-to-sequence modeling. So you may tell me you can ask me what is a sequence-to-sequence modeling. So it's just two RNN models. So, but instead this RNN, right, instead of this RNN actually generating like memorizing information of the sentence itself, that text sentence itself, it tries to like encode and decode the sentence. So you think of this analogy as if you want to translate, okay, so let's say you want to translate from English to French, right? They'll need to first convert all these like words into numbers suitable to for the robot to understand. So again, robots understand only numbers, right? Then these numbers will be called like S. And then when I pass it to the decoder, it decodes these numbers into the suitable language to be used. So I say again, encoder tries to encode those like sentences, right? Your text sentences into just numbers that represent the words, and you're using that numbers to put into a decoder, and the decoder tries to interpret these numbers into another language. So it's a bit like they how they got this is a bit like a translator lor. They think like a translator, or I know like both languages, but what's going on behind the scenes of someone hearing English and can speak Chinese to another person, right? So this was one of the ways that was being proposed. And so actually, right, if you think about it, sequence is the one of the simplest methods to represent how translation actually works. But later they found out that in like ChatGPT or in Google Translate, it wasn't that effective. But you'll see, we'll see why later, or even in day three, when we talk about the actual ChatGPT. But that is just a very good starter to show how it was initially developed. So, what do sequence do, right? Is machine translation, which today's lessons focus, right? Sorry. Then text summarization is you could actually use the sequence to summarize uh text like how ChatGPT does it lah. So it's like your initially like your ChatGPT also, and it can also do speech recognition, but we won't cover this today. So you could see how it already has this out of all these three use cases, it has one common one common thing in common. So I pause for 5 seconds, I let you digest this slide, and then I'll just go on. Okay, so what's common within these 3 points, right, is translation, right? It will try to convert an input and then output. So text summarization also, when it inputs, right, I input in a large sum, a long chunk of text. But when the outputs is actually a very short text. So text summarization is like input output. So again, two RNN, one RNN to do the take in the input, convert the numbers, and now RNN take its output, take the input from that previous RNN, right? That RNN itself to summarize what's going on, output out the answer for you. So again, input output, and even speech recognition. In speech, right, it's only two columns, right? Known as two columns of data. We only have amplitude and frequency. So whenever we speak, right, there will always be a certain frequency, and the amplitude is how loud it is. So probably the loudness could, in a sense, give context to what the speech actually is. But then frequency is like how high pitch or how low pitch it can be. So using these two columns, I'm just giving a very simple example. Using two columns, we can convert these into suitable numbers to be interpreted. In order for these numbers to be interpreted into like actual like recognition. So recognition is like I can recognize whose voice is it, etc. So again, input and output. So to summarize it, these three covers input output sequences, which is our main focus for today. Even the practical later, we also cover some input output also. So machine translation, okay, we are now zooming into what is machine translation. It's introduced by Seq2Seq, I may not pronounce his name correctly, in 2014. So in 2014, I think it wasn't that quite well developed as today with the ChatGPT we have today. But this is just a foundation that 2014 has laid for us. So it consists of two RNNs that we discussed just now, like Cindy discussed about how those basic RNNs could work. So again, encoder, decoder, and then they are particularly effective in translating sequences within languages. So for machine translation, right, the encoder, decoder tries to process source language and captures the meaning and then generates the target language, like I mentioned just now. And they also use this thing called attention mechanism that focus on the relevant parts of the source language for each target word. For better translations or long sentences, okay, with this one, we will cover later on attention mechanism because um it tries to basically get the most relevant words that's suitable for the sequence modeling. So attention is like how much attention must I pay attention to each word. So I assign it to a number. Imagine you know in machine learning, right? It's all very quantitative in a sense, which is why attention mechanism aims to do, which is numbers, converting words to numbers. How important is a word, right? How much attention must you put it into a word, which is you assign it a number, not its weights. Okay, um, this equal architecture is fundamental for this modeling, and it translates lah. So like one example that this slide tries to show is the cat ate the mouse in English to le chat. I don't know how to pronounce la souris in French. So imagine it tries to put like translate, but it will not have every word like it's being captured. You see, so it's like 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Maybe in this case it's only like five words to 5 words. But then there will be times where it doesn't have 5 to 5. It can be like 5 words put in and then 4 words come out. And again, within that itself, we are trying to explain as much as possible, as simple as possible, this thing in between, like what's going on, right? But then actually, if you really want to study, actually, we really understand what actually is really going on, and it's completely normal. Like even people who are working on ChatGPT, right? They are actually unable to really understand what's actually really happening within that black box, terminology black box. Like how is this like happening? Okay, so even if you don't understand, it's completely normal, and yeah, we hope we will try to like deliver as simple. So like quarter of Seq2Seq, right? It tries to capture um input sequences and transforms them into a fixed dimensional context vector. So it processes input sequentially to generate a representation for each token. So simply what it means that tokenization just means I separate uh, every sentence into words. Like we love NLP, right? We is a word and love is a word. So NLP is a word and the exclamation mark is a word. So we are essentially breaking them down into their suitable words, like breaking down from digesting food into like smaller parts, so that these smaller parts could be used in the next step. This is only step one. I'm just breaking down a sentence into simple words, very simple. So this one, okay, this one you may seem, whoa, it's very complicated already. Like you could tell me like we're suddenly talking about coordinates like axes. Okay, but I guarantee you it's actually very simple. It's simply just representing word context into x and y axis. So um for words like man and woman, right? You could see why they are having like polar opposites. Man is the opposite of woman. So they are actually being put as opposites of the gender coordinate. So after I tokenize into like we love NLP. So we is a word and love is a word. So NLP is a data point and exclamation mark is also a data point. So we have like 4 data points to actually work with. So grandfather, right, and boy, definitely grandfather's age will be a contrast of a boy's age. Because a boy, we can think of it as like a 20 years old boy versus a 90 years old grandfather. So there's a in the modeling context, it's a contrast in terms of how we separate, how we want to interpret what grandfather means and versus how what boy means. So I give two examples, man and woman and grandfather and boy. And then again, gender, since grandfather and boy are like male gender, so it'll be like one. And then woman and girl are like another gender, so it's like, and then again, polar opposites. Then in between, we can even have things like adult, child, and infant, which means we are, what to sum up, we are actually representing these words into coordinates that are very understandable for the model. So I give you only two numbers, A, comma B. You could already tell me what is that word, right? So I give you like, let's say I give the model 10, comma 10. So I'm giving the model 10, comma 10. So that's essentially just a female grandmother, old grandmother. So because age is 10, so 10, comma 10 is like old grandmother. So again, you could see unseen data, like the model understands what 10, comma 10 is without even looking at it, without even getting trained into what is 10, comma 10, because it's already trained based on other data. So even if it sees like unseen data, it kind of understands, it uses its best knowledge to try and understand what 10, comma 10 is, which is grandmother. Then sequence can even use like 50 dimensions of it. So of course, this was reduced to 3D because uh, to be realistic, it's not very possible to visualize 50 dimensions in the uh plotting. So in this case, because we want to make it like even more details to capture, you see, it's not just age and gender, but rather like 50 other dimensions. But then of course we want to visualize it, you can only visualize it as an XYZ axis, a 3D axis. I'm pretty sure is you can think of it as your Fleming's like right hand rule. I'm pretty sure Jungi knows it, right? Your engineering, you definitely got to teach this thing. I always like to use this analogy to show what does the three dimension mean, because it literally describes a bit like how a 3D model could work. So in this case, we can think of it as like this, but um using only three axes, right? We could in a sense understand what is a body part, what is a group of body parts, what is a group of feelings, a group of relatives, even groups of city, right? Which leads me to my next slide, which I actually hidden that. Oh, that one is another PowerPoint. Apologies. That one is another PowerPoint. We will learn like the additional stuff tomorrow, but like just for now, it's just this. Just know that you could do like 50 dimensions of this to represent it even clearer to the model. Then lastly, we could do like encoding hidden states. So remember, RNN calculates a new hidden state at each time step based on the previous one. So remember RNN theory that Cindy covered just now. So this continues iteratively for each token in the input sequence. So if you refer to the animation to show the Swiss and add to the end. Okay, it just pumps in time step 3, pumps in, and it outputs a hidden state 3 to be put into the encoder. So hidden states refer to simply the information it has learned bit by bit. Okay, hidden state. So the first one is the and the second one is just Swiss, and the third one is just Swiss at to the end. And then you just pump in each word by each word, and then you produce a hidden state to be put into the encoder to do it. So this is the iterative approach. It's like your for loops, you can think of it, right? So this will be modeled into like suitable numbers for the model to interpret, which leads us to our decoder. Okay, decoder is, since we already understood like the encoder stuff, right? Decoder is actually just a repeat of the encoder, but now we are doing the opposite. Instead of trying to convert them into useful like numbers, right? We are trying to do the opposite. We are converting useful numbers into the words that we want to output out. So these word embeddings, right, are transferred to this decoder, like over here. And the decoder forming another set of numbers suitable for feed-forward neural network. So feed-forward neural network, if you think this is a new terminology, actually it's just day 1.1, your basic neural networks. It's literally just that, but people try and say FFNN, feed-forward neural, is because it sounds more fancy in a way. So you're not required to know how and why decoders turn encoded these encoded numbers into these state numbers. Again, uh, this is actually a black box. Like we don't need to know why or how these nitty-gritty details are in, but just know that for these word embeddings, they are being transferred into the decoder, which is basically they call it the context vector lah. And then you are just pumping it into this big neural network to actually output the final prediction. So I always like to give analogy of this example here. So it determines the most probable word given all possible words generated. So ever wonder how ChatGPT tries to generate word by word? Whenever you type ChatGPT for your assignments, right, they will always be like, so how are you? And then it outputs I and then M and then fine. So ever wonder how this could be achieved? So how it was achieved is actually this example lah. For so it has trained based on three words. So it actually a very simple model known as vamos, and E. Vamos and E is like three different probabilities of what is supposed to output. And then is 0, vamos is 1, and E is 0. So after passing to this uh these word vectors, right, to suitable vectors that are being input into this for neural network, you see that these two numbers actually could represent what is the representation of how this could be formed, because you are actually giving this neural network, right, suitable data to be actually put into the suitable neural network. And then based on these two numbers, it could effectively describe the whole output known as softmax. This is actually softmax. Okay. New terminology. Softmax refers to how probabilities of each word are being outputted. So example, vamos and E. Vamos has the most probable 100%, I'm very 100% sure that I want to output vamos, and hence this people neural network understands it needs to output vamos, and hence it outputs vamos. So you see how it's being derived, and the next ChatGPT will output vamos. So vamos, and E. So at each time set it's like this is 1 is 0 0 0, and then 0 1 0 0, and 0 0 1 0. So this reminds us of like binary numbers, yeah, ones and zeros. And essentially it's just binary numbers, because 0 represents 0 probability and 1 represents 100% probability. So you just keep outputting based on this theory. And we go to our training of the architecture. Okay, this is quite simple. It's just y is what's your name, and y the input is what's your name, and the output is y prep. So in statistics, it's quite y prep. Okay, but don't have to worry too much of the fanciful notation for now. It's like quel s ton nom. And this error is being calculated between y and y prep. And it's actually, you can call it like cross entropy loss. Okay. Basically, it's just how the model learns from backpropagation. Yeah, if we go through like day 1.1, right, we talk about how the model learns its lesson. So called learns its lesson after knowing that it has gone through a wrong answer. And then it's like, okay, I know that I outputted the wrong thing, and hence I'll go and change it. So this is not as like cross entropy loss. Okay, but don't have to worry about the term for now. So it's just like now it's just the softmax is just a repeat of what was going through just now, which is generation advances by picking the next token if the probabilities of the decoder. So you could think, I could always like to think of it as an MCQ question. So in a test, right, when we want to like, when we are stuck with a question, okay, let's start with a question on our paper, exam paper, and it's like a multiple choice A, B, C, or D. I don't know what to choose. I don't know whether is it A or is it B, but I know C and D is wrong. Right? I know C and D is definitely wrong, but I don't know whether A or B is correct. But definitely C and D not the answer. So I will try and output probabilities of each. What is the most probability given my human brain, the centers of my human brain, which is my neural network in this case. So what is the best probable answer? Like I go and think of my revision, of how I revise my work. Which one is A or B the more probable answer? And then I will try and shape that correct answer. That the most probability one, even though I may not be sure it's 100% correct, but I'll still do it. And then when I get back my test paper, I realized that my teacher circled A instead of B. So I got that question wrong. And then that's not as bad propagation, because that's the error that's being calculated. You see that, oh, I got this question wrong. And then I'll go and change it. Next time I take note there is A next time. So your neural network takes into account that A should be the answer instead of B. So the softmax output will then during later stages, it will output A is the answer. So it's just that. Okay. Now this is the most so far this is the most complex part for a new student. Um, you see this is known as the heat map. Okay, so imagine the intensity of colors. We do quite hue. In I think in IM they have this thing called hue. So um unimportant is white, but then important is actually very dark colors. So important, the darkest color, and then this be the neutral, not unimportant, not important. So it's just in the middle, you know. Then now it tries to enable this known as attention mechanism because it enables the model to assign varying levels of importance to different parts of the input sequence to improve translation accuracy. So they introduce this to actually assign which which word is actually more important compared to every French word. So it tries to assign the importance of it. So in this case, how was your day, right? This is how was your day? How was your day? It's actually this whole phrase compared to every word. So you can think of it as a nested for loop because each word itself is one for loop. And then this is also another for loop. So it's a nested for loop, Then it's just how was your day? So how and what's and your and day. So what's the importance of how in the word comment in French, right? It will be the most important. And then was and so will be this is the most important. And then this also has a lot of importance. So it will try to use other algorithms to further calculate, which we won't cover that. So that's ta will be like your and ta, and then journey will be like they. So importance, the level of importance when it's compared to to another word is known as attention. How much attention must I pay attention? So you must pay more attention to how, must pay more attention to was. So this was one of the algorithms that is being worked on based on the soft max probability. So this is actually it's a soft max probability function that actually uses the best probability, like the MCQ example I gave just now. And even attention mechanism workflow, right? You see how this associated each word in the input sequence, and each hidden state is assigned a score based on relevance to the current decoding step. Hmm. The hidden state is just the RNN that we demonstrated just now. So it's just in a sense how the it learns lah. Don't need to worry about this for now. But all I can say is that you will try and pay attention to each word and see how important must each word is in relevance to the translation. So of course, this will be have certain like limitations of the encoder decoder sequence. So the decoder receives one word at a time from input sequence. Okay, so how are and you? I think actually that's why I think ChatGPT wasn't able to function as well because of this architecture, like that the way it's being done, the algorithm is done. Okay, so only the final hidden state of encoder, right, is past the decoder for processing. So it's like after I try and like encode give it so use useful numbers, I then pass it all the way to like all in one go to the decoder. So I think that was one of the limitations of the sequence. I think that caused certain problems that which we won't cover also. And then this approach, right, is actually not it doesn't effectively align towards in source and target languages that leads to less accurate translations. Like I said, like it simply just doesn't even work well, which is why transformers was that's why ChatGPT generative pre-trained transformers. It's not generative pre-trained sequence to sequence. If not, our ChatGPT will become ChatGPT Seq2Seq, which is not the case, right? So transformers was one of the architectures that we will be covering on day three lah, to mitigate the challenges based on Seq2Seq models. So we now do a short like practical. This is the although this uses transformers, like you can argue that, oh, why are you giving transformers, right? But then it does a very close approach to Seq2Seq approach. It is why we could give it a try. And then if you are interested in coding out the sequence from scratch, right, you could do that. There will be websites to guide you through. Okay, but for today we'll just do a simple one. Transformers is a very simple one. So I'm gonna share my uh collab. Great. So could y'all, I give you all like 3 minutes, you could log into your Colab, just search here, search Colab, open a new notebook or anywhere you could jot down notes. So assuming that you have been logged into your Colab right now, you could see this. Okay, so again, the notebook title, let's not care about that. We will care, fine. We will change it to like day 2.2, 2.1, Gen AI sequence to sequence modeling. And first, we'll start off with importing the necessary libraries. So we'll call form transformers, import Marian empty model. So Marian empty model is just a way that it was the proposed pre-trained model that's used to do the task. You could read up more on it on your own. So if you are asking, why is there the gray color text, right? Actually, it's because that I have it's probably because I have Colab Pro, which is a subscribe feature. So if you don't have this gray color text, not to worry at all. It's completely normal. You will just type like not as how you normally type your code. So you first do a model name. So model name is just a variable that you want to save the model to. So we call it Helsinki NLP Opus. MT stands for the Marian MT model, English, French. So English, French, ENFR. So you're importing the specific model that translates from English to French that's been done by other people. This is known as uh, pre-trained transfer learning or pre-trained models, which we will do a somewhat do in day 2.2 as well. But now you just need to know that someone has done that model for you, and then you're just using the work of other developers into demonstrating what a Seq2Seq model is, which tokenizer equals Marian tokenizer dot from pre-trained model name. So this allows us to tokenize each word like we run through in one of the slides, right? We tokenize we love NLP to we and love and NLP and exclamation mark, like breaking them down. So the tokenizer is a tool to help us to tokenize to do the action. So by using instantiating a text, right? How are you? We're actually passing this text into the tool called tokenizer that helps us to tokenize the text. So it's a parameter to pass in and then you output you like the tokens, right? Return tensors equals pt is just a way to return the tensors, but we won't do in depth now. Okay, now we'll just save this under inputs, and we will try to print the inputs out. You see, you can do it. Return tensor equals pt. Mistake. So you can see, right? When you want to print out, whenever you want to troubleshoot the code, you try and print out what's going on. So you'll see like, okay, the input IDs are hello, how are you? And these are what's being put into input. And then attention mask is just the attention mechanism that I've said just now, but they have applied their own way of doing the attention, the self-attention thing. Okay, again, it's a very black box which you won't like cover too much. Just know that these are the useful numbers that we're talking about that can be used by the model. And then now we'll try to make use of the inputs, right? Model equals, you instantiate the model that we instantiated, Marian empty model dot prompt retrain model name. So model name refers to this Helsinki NLP Opus, right? Okay. Then outputs is the model.generate. This is the code that actually help us generate. It does one line of code. So that's the beauty of it, of pre-trained models, because it does everything for us. Cool. Inputs, which allows us to visualize its outputs. If you want to print out outputs, I think it's not possible. Oops. The outputs equals model.generate inputs. In that case, you are unable to print its outputs out because it's still it, it doesn't have attribute to help us print the outputs. But don't worry, we will just do the tokenizer dot batch decode. So batch decode is just decodes this whole output thing they were trying to talk about in a batch. Skip special tokens equals true, right? And then bracket 0. And then lastly, you try and print this translation out. Strange. It works here. Give me a moment. Inputs, outputs equals to the model dot generate. Inputs. Oops. A K. Oh, my mistake. Return tensors plural. I put as singular. So that's the mistake. Other than that, you should be able to work. So it translates to a successful translate to bonjour comment Alice Wu. So we try and translate bonjour comment Alice Wu. So bonjour means hi. That's like quite common knowledge. So translate to bonjour, good morning, how are you doing? So hello, how are you? Good morning, how are you doing? Is actually very similar context. So this is how the single sequence models is able to capture meaningful meaningful words and their respective meanings into numbers. And then I'm just able to capture that numbers and outputting it out in a form of another language. So that will be the end of my demonstration. So the error just now that we faced was just return tensors. Again, plural. And then again now if you want to like print out the inputs. And we'll just put it here. Sure, you have these numbers that are being printed out, and model and Marian empty model print outputs. Sure, you'll be able to print the outputs. Yeah, we are not able to print these outputs, which is again output into again very useful numbers. And then bonjour comment Alice would be the translation based on the output. So these outputs with this in these numbers, right? We will decode the numbers into this. Yay, so that will be the end of our demonstration. I hope you got a good insight of how the theory could be linked to the practical. Okay, I hope I won't bore you with the theory details any further. So now I will just simply go through a beam search, but I will just go through very briefly because this is optional. So beam search is one of the methods that try and help these sequence models on how it actually gets a more quality results. So if you have taken data structures and algorithms, it's a bit like your software engineering. Okay, I'm a data science student, so I may not be able to describe how DSA exactly works. I may not be able to know those details, but I know at least it's very similar to the search algorithm for data structures and algorithms. So by exploring multiple potential sequences simultaneously, you will be able to increase likelihood of finding high quality translations or summaries. So I'm going to give like an example, okay, of a binary tree. Actually, it's not really a binary tree. It's like 1, 2, 3, 4, 5. Okay, it's like five. Uh, what do you call that? Five leaves, five of the child nodes and stuff, and then you're just going from A to A B. So again, you're combining possible combinations of whichever it tries to combine, and then it tries to see whether the probability matches. So it just to tries to highlight the best two probabilities of it. So first position is select stock characters, and then it tries to combine that probability for character pairs, and then extends to character triplets. And then you go on and on until the end token that's selecting the best sequences. So you see the best sequence will be the A, B, C, and A, D, and then N and N. So the N is simply an N token to simply say show that it's the end of a sentence. Right, so A and C, and then A, B, A, E, A, B, C, A, E, D. So you're building up based on A to A, B. You're filtering up, the C is being filtered out already. C filtered out, so it's just A, B, A, E. And based on these two, I'm developing these two into A, B, C, and A, E, D, based on the combinations that I can have. What's the best scores, and other things like that. So I hope this gives an understanding of how uh, these translation models could give us the output us the best probability or the best answers that we may want to have. So it's just going through some of this beam search. Okay. So I won't be covering the details. It will just be this. And these are the references for the practicals or the tutorials that the teaching team has kindly prepared for. So now is 11:40. We are actually quite ahead of time. We have 20 extra minutes. Okay, originally lunch break is supposed to be at 12, but if since we ended early, we'll have like early lunch break. So we'll have until 1 o'clock. We just come back at 1 o'clock for our day 2.2, which is the practical section of the sequence model. And then in the practical section, we'll be doing deploying the Discord bot. So you'll see how we can make sequence models from scratch. And using from that model from scratch, we are doing it on our own, and then we are also coding out the parts where we are deploying on the Discord bot using async libraries, etc. So we hope to see you in day 2.2.